Okay, in this video, we're going to talk real quick about the mechanisms of how concrete are going to work. And when we look at concrete, there's a history timeline of different types of concrete that we have. And a lot of times we refer this to cement because concrete and cement are two different words. Cement is a part of what makes up concrete. Now, when we look at cement in early time histories, maybe like the time when we made pyramids, we were using things that were considered non-hydraulic cements. And to do that, we were using lime. Now, this is nice because it's breathable, it's somewhat flexible and porous. Now, when we talk about these non-hydraulic type cements, we may want to watch out if we're using modern day concretes to do repair on these because they're going to have different properties and they may end up tearing each other up. Now, when we look at modern cements and we think of the Colosseum here, this was held together with volcanic ash, and this is a hydraulic cement. Now, hydraulic cements set up and harden by chemical reactions with water called hydration. So we're going to talk about hydration here in a minute. Our modern concretes that we're using now use something that's called Portland cement. And a gentleman that invented that named it Portland after some of the rocks and the materials by the color of them from his home country that he was from. And so when we talk about concrete, concrete is made up of water, Portland cement, which is right here, and then a mixture of sand and aggregate. So we have sand here and aggregate. Now, the different ratios that we mix all these can change the strength and the properties of the concrete quite a bit. Now in lab, what we're going to do is use a basic method called the 3-2-1 method, where we're going to take 3 shovelfuls of the aggregate, 2 shovelfuls of sand, and a shovelful of cement. And then we're going to come in and start mixing in the water. Now when we get in the lab, we'll show you the consistency that you need to have to make that concrete. And part of that's going to be tied to the slump test. So let's talk about this hydration process and the compounds that are going to form in this chemical reaction. Now I want to talk about this chemical reaction right here. This is where we're going to get all the bonds and everything forming to give the concrete its strength, and there will be some heat that is produced through this chemical reaction because it is an exothermic reaction. And these are just some of the major components that are going to be, or compounds that are going to be generated. The first one is going to be CSH, calcium silicate hydrate. Now, how do we describe this? If I was to look at it at the micron scale, take it to a microscope, we would see that it would look very spongy-like, kind of like coral. Now, this is an amorphous material, meaning it doesn't have a repeating structure, and this is what's going to give concrete the majority of its strength. So we really love CSH for its ability to give concrete its strength. The next product we're going to have is going to be considered CH, which is calcium hydroxide. Now this is kind of like the savior to concrete in helping protect it. Now let's talk about concrete here. When we have concrete, it's going to tend to want to crack, and it likes compression and not tension. So what are we going to do to help reduce the cracking and improve the properties where the tensile loads are going to be? We're going to add steel rebar, and that's part of this lab. We're going to have unreinforced and reinforced samples, and we're going to be testing those. So when we put steel in concrete, it would want to rust and corrode. If it's encapsulated in the concrete and sealed by the concrete, it will not corrode, because what's going to happen is we're going to have iron hydroxides form due to the fact that the pH level of the CH here is going to be very high. We're talking 12 to over 13 on the pH scale. So you guys had chemistry where you talked about acids and bases, and yes, both of them can cause a burning sensation. So when you're in the lab and you have the concrete, you might sense that if it comes in contact with your hands because of that high pH. So be sure to wash your hands properly. Now, when we talk about the next structure here, there's actually 2 of them we're going to kind of talk about. And we're going to have the AFT form, and then it's going to get consumed and become AFM. So ettrinite, which is going to look like these whisker materials coming out, pine needles growing out, filling the voids in the concrete. Now what's going to happen over time is that's going to get consumed and become AFM, calcium monosulfide aluminate. And that's going to form a structure that's going to have these little plates like this organized kind of like a rose rock. And that's our state flower for Oklahoma. So these are the products that are going to form over time. Here's our hydration timeline. Let's look at this graph on this side first. This is just an approximation of the amount of compounds that we're going to generate over a logarithmic plot here. And so the first few minutes, not much is really happening. But after a few hours, we start seeing the ATF forming, and that's going to give us our initial setting and hardening of the concrete, or setting up. What's happening is the CSH is starting to grow and develop, and that's going to take a period of time, at least, let's say about 28 days, to cure, to set up. So 28 days is important here because if I order some concrete and I pour a foundation for a machine to sit on, or I want to run some heavy equipment over that concrete, I may want to wait at least 28 days before I put any heavy stress loads on that concrete for it to hydrate out over time. Now there are additives and things we can put in the concrete to decrease that time. Quick cure concrete. Now this plot shows our ATF and then being consumed and coming into our monosulfates right here. And so over time, we're going to see the curing of the concrete. Now, most of the hydration of our concretes reach about 75%. And again, over time, they slowly can hydrate more. That's why they say that the concrete will continually get stronger over time. But the majority of it is done within the 28-day time frame there. Now, when we look at concrete with rebar, and we've got rebar right here, we need to talk about rebar. First of all, rebar is going to be made out of steel. And we have an ASTM standard that we can have different steels. That's going to define the alloys that the steels are going to be made out of, resulting into our yield strength. So if we have a 615 bar, it's going to have a S marked on it, and it's going to have a 60 KSI yield on it. Now, to transfer the load from the concrete to the rebar, we're going to need these little bumps all over the rebar, and that's going to allow them to bite and hold each other mechanically right there. Okay, so those are very important. We can't just use a smooth bar of steel as rebar. We're going to need the texture on there. And again, the bars are going to have the stamping on the material. Now, we talked about the fact that concrete will help protect the rebar. But if we remove down here in this photo the concrete, it can become exposed and it will rust fairly quick. Over here we have a picture of concrete that was just broken during a demolition job, and we have this white compound on here. This is the iron hydroxides that were formed because of that high pH that protected that bar, and we don't see the rust on there. Now that it is exposed, we're going to see corrosion taking effect on that bar. So rebar sizes, we're going to be using a number 3 rebar in lab. So the number rebar times an eighth equals the diameter. This is pretty much true up to about an inch in diameter of bar, and then they have a little different method, but let's just worry about inch and under for this lab. We're using number 3 bar, and we're going to be placing that into our concrete. So here's just kind of a little bit of common uses for the size of rebar. So number 3 would be a thin, cost effective. It's going to add strength to concrete, road, driveways, paveways. So this is a real common rebar, and it's great for engineering science labs as well. Now in lab, you guys are going to be pouring 2 different kinds of samples. The first one is going to be a cylinder. It's going to be 2 inches in diameter, and it's going to be 4 inches long. Now, when we make these in lab, we're going to take out the bigger chunks of rock, the aggregate. We're going to just want pretty much the sand and cement to go into this cylinder. And we're going to have these little PVC cylinders for you. And one hint that I would like to point out, just looking at the texture on the surface up here, this one has a lot of big bumps on it, and this one is fairly smooth. When you guys screed this off, that means when we level it off and everything, try and get it as smooth as you can so that when we put it in the machines to test, this surface is flat. We do have a tool that'll help knock some of this down, but it also helps if you take a little time and do a good job screeding your concrete off there. Now, the next sample that we're going to be making is going to be a beam with and without rebar in it. And so this beam is going to be about 16 inches by 3 by 4 inches in size. And we're going to be doing a flexural test on it where we simply support it out here. We're going to put a point load in the center, and we're going to come in and we're going to see that concrete break as a brittle object rather fast. Now, once we put the reinforcement bar in there, we're going to probably see potentially more cracks forming, but that's not breaking as much because that bar is taking that load, and then eventually it's going to fail. So the machines are set up to tell us the point that it's reached its maximum load, and it'll give us that data. So that's pretty much it for this portion of the video. Just wanted to take a little bit of time about the products that we're going to be making and what we're going to be seeing in lab.